In our complex society, there is a need to establish a method for creating data based on some knowledge about an environment that allows for decisions to be made based on the results of the data. Simulations are a very effective way of handling that need because they are relatively inexpensive, present little chance of actual danger, and can be repeated as many times as desired. Allow me to give you a non-mathematical example of a simulation that is used quite a bit. That is the simulation called the Airline Flight Simulator. Pilots must receive practice in emergency procedures, for example, flying in a thunderstorm. And it would be very impractical to have a group of pilots hop into an airplane, one of the airplanes flown by that airline, fly up and seek out thunderstorms, and fly into the thunderstorm and see what happens. And if nothing happens, then turn off some engines or lose electrical power. If you did all those kind of things, probably what would happen is the airplane would be damaged, if not would crash, and the pilots and everybody else aboard that airplane would probably be injured or be dead. Very expensive, very unnecessary, because we can use the flight simulator. In an aircraft flight simulator, a pilot sits down at something that looks exactly like the cockpit of the particular airplane he or she is flying. And the instructor is able to put them in situations, thunderstorms, power outages, loss of avionics, etc., that will test the pilot's ability to handle that situation. And if the pilot, of course, messes up, it's an instructional situation. We go back and we talk about it, and then, once again, they try it again. And as long as the pilots have these simulators and can repeat the process until they understand what they should be doing, then we don't have to worry about airlines flying planes into thunderstorms. It provides a realistic opportunity to simulate a real environment and to get results. Another quite interesting example, it's a personal example, is that in the Air Force, I was a B-52 electronic countermeasures officer, and obviously we couldn't test our electronic countermeasures against live Soviet weapon systems, because I don't think the Soviets wanted us flying our bombers over Soviet territory, and certainly they wouldn't want to reveal their particular tactics. So we'd fly in a simulator. And when I was in that simulator, I might have been over some target area, flying against certain types of weapon systems. And if I messed up, the instructor could point out what I should have done, what jammers I should have used, or what strategies I should have used. And therefore, I was able to simulate a real environment without actually having to put myself in a dangerous situation. Very effective. But now let's talk about mathematical simulations, since this lecture series is about mathematics. They are very effective, provided we understand something about the probability of the situation we are attempting to simulate. Some examples would be traffic flow on city streets or on highways that can be simulated with numerical values if you know probabilities of certain outcomes on those streets or highways. Business strategies can be tested using simulations based on probability information available from past performances or through sampling. Tactics in various sports can be simulated using team tendencies and success rates. A number of years ago, I went to a talk by a gentleman from the Green Bay Packers, and he was talking about how they used computers to evaluate tendencies both of the Green Bay Packers team and of the teams they were playing. And obviously through simulations, kind of like board games or video games, they could test various tactics versus possible opponent tactics to see what the results might be. All in a probabilistic situation, all in a situation where we're not actually playing games, people aren't being injured, we are receiving interesting data that can be used to make decisions. Weather can be simulated mathematically using probability information gathered in seasons past. Medical experiments can be simulated using data from past experiments. In all these situations, we are using probability information, mathematically simulating real-world situations. The key to a success of a simulation process is the design. Like anything else, something that's poorly designed will not provide interesting and adequate information. There is a simple 5-step process to produce a simulation. Let's take a look at that process. The process requires that you have complete information on the types of outcomes, the probability of those outcomes, and the nature of a trial. And if that is known, then we're ready to start the five-step process. The first step is to state the nature of a simple event in the process. That is, what is the simple event that we can break the process into, and define the possible outcomes for a simple event. An example of a simple event might be one sales call with a possible outcome of no sale, a sale of $100 worth of product, or the sale of $1,000 worth of product. So we'd have a simple event of one sale with three possible outcomes. The second step in the design process is to quantify the probabilities for each possible outcome defined in the first step. In our example, the probability of 0, no sale, is 0.6. The probability of sale of $100 worth of stuff is 0.37. And the probability of selling $1,000 worth of product is 0.03. Notice that the three probabilities sum to 1 because there's no other possible outcome. The next step is to select a probability tool that would simulate the probabilities indicated in the previous step. In this case, we would probably use a random set of digits, or random set of numbers from 1 to 100. The numbers from 1 through 60 would represent no sale. The numbers from 61 to 97 would represent a $100 sale. And the numbers 98, 99, and 100 would represent the $1,000 sale. You'll notice that 1 through 60 has a 60% chance of being selected if you have 100 random numbers, and that was the probability of getting no sale. 61 through 97 has a 37% chance of being selected out of 100 random numbers, and 98, 99, and 100 have a 3% chance. So we've matched up the outcomes of our probability tool to the outcomes and the probabilities of our simple event. It is vital that each of these outcomes from the simulation tool match. If they don't, then you have a simulation that is ineffective. The next step is to define how many simple events complete one trial. In our example, we expect our salespeople to make 5 sales calls in a typical day. We would say that N, the number of simple events in one trial, equals 5. The final step is to define what is to be counted or recorded or measured possibly at the conclusion of each trial. In our example, we would count the number and type of each sale and then record the total sales for each day that we simulated. Notice we could simulate millions of possible days for our salespeople and get a pretty good idea of what our expected average sales over a period of time should be. This is without a single sales call. We can do this to check out, for example, possibly what if the salespeople made 6 sales calls or 4 sales calls? How would that affect our total sales per day, per week, per month, per quarter, etc.? A very useful tool, and on a computer, millions of simulations can be done in a very short period of time. Since the value of a simulation depends on the ability of the selected probability tool to replicate the outcomes of the simple event, choosing the tool can be quite important in the design process. If the simulation involves 2 outcomes that each have a 50% chance of occurring, then a fair coin can be used. Simply having 2 outcomes is not enough to justify a fair coin. They each must have an equal probability. If the probabilities involved are fractions that could have a common denominator of 6, that is, fractions of halves, thirds, or sixths, we can use the common 6-sided die. Spinners can be used for almost any type of probability as long as the spinner is designed to produce the required probability outcomes. A printed random 10-digit table could be used to simulate any decimal probability. Digit tables can be used to simulate almost any probability if the appropriate digits are in the table, and we regard only digits that are useful and disregard the digits that we could not use. A random number generator on a calculator or a computer probably is the best way to go if you have one, because we can generate strings of random numbers to meet the needs of our particular simulation. A basic simulation would involve something we've referred to in the previous lecture called a Bernoulli trial. And once again, we probably need to look at our picture of the two Bernoullis sitting around doing math problems when today's adults would probably be watching TV or listening to music. And perhaps they were listening to music played by someone off the screen who's playing a violin as they work math problems. But quite frankly, I jest about the Bernoullis, but they were quite brilliant in their use of mathematics and in their investigation of physical properties. A Bernoulli process, you may recall, will have two outcomes, and only two outcomes. And these outcomes we label success and failure. Since the events are independent, the probability of success, P, and the probability of failure, Q, will not change from event to event within the trial. And again, the Bernoulli trial was named after Jacob Bernoulli, who analyzed this type of probability around the year 1700. He wrote a book entitled Ars Conjectandi, and in that book he analyzed situations which are now called Bernoulli situations. There are three types of Bernoulli trials, one of which we've talked about in the previous lecture, the binomial. But there's also a geometric and the negative binomial, which can easily be simulated, all three types. As was defined in the previous lecture, a binomial trial is a Bernoulli trial with a fixed number of simple events. Okay? The trial ends at the 5th event or the 7th or the 10th or whatever it is. And an example of that, the one we could easily simulate, would be a situation where a family is planning to have 5 children, and we want to know what the probability of having exactly 3 girls among those 5 children. Not a very important question for most people, but it's a valuable simulation because it's simple and we can understand how we use simulations to come up with an answer. So let's take a look at it. Let's go to our 5-step process. Step 1, a simple event, is one child. The outcomes, B for boy, G for girl. Step 2, the probability of having a girl is 0.5. Actually, the probability of a girl being born is slightly less than 0.5 because the probability of a boy child being born is slightly greater than 0.5. But it's so close to 0.5, for our purposes, we will use the 0.5 or 50%. What type of tool can we use? Well, a common tool would be a coin. And the outcomes, head and tail, must be assigned to the two outcomes in step 1. So we'll say a head will simulate the birth of a girl. A tail will simulate the birth of a boy. Step 4, define a trial. This is a binomial trial where n equals 5. The number of simple events, the number of children, is 5. And at the end of each trial, we will count the number of girls. Obviously, the number of girls will be 0, 1, 2, 3, 4, or 5. We can run thousands, if not millions, of these trials, and then look at the results for the number of times we got each number of girls and predict the probability of this family having 3 girls and 2 boys among their 5 children. Now, the question, of course, is, are there other situations using something like this? And the answer is yes. What, for example, if we wanted to know how many children the family would have to have until the first girl was born, and then the family would stop? Well, this is a Bernoulli trial that's called a geometric situation. A geometric situation is one Bernoulli trial, that is, there is 2 outcomes. They're independent. Each event is independent of the previous one or the next one. But the difference is the trial continues until we get a particular success, our first success. In this case, the success is having a girl, and therefore we would go until we get the first girl. So let's take a look at steps 1 through 5 in designing a simulation to see how many children on average a family would have to have before the first girl arrived. Step 1, a simple event, is one child being born. Okay? Step 2 is the probability of a girl being 0.5. Notice we haven't written down the probability of a boy, and that's because we know there are only two outcomes. And if one is 0.5, the other one must be 1 minus 0.5, since they are complementary outcomes. Step 3, we're going to use a coin once again. Heads is girl, tails is boy. You'll notice that step 1, 2, and 3 are identical to the binomial simulation. But step 4 is changed. We're going to go until the first girl is born and then stop the family. And instead of counting the number of girls, we'll know the number of girls in this family, 1, we're going to count the number of children. Notice in these cases, we can do, like I said, thousands or millions of simulations, and we don't even have to wait 9 months. And in a short few hours, depending on the speed of your computer, you could look at this and make some interesting observations about the distribution. How many times did it take 47 children before you got the first girl? Now, of course, I don't think most families would go that route. It's probably give up after 5 or 10 children. But again, we're dealing with mathematical theory, and theoretically, one could have an infinite number of births before that first girl appeared. But the probability of that would be very, very close to 0. The third type of Bernoulli situation that we can simulate is a negative binomial trial. This is a Bernoulli trial which concludes when we have a certain number of successes. A simple negative binomial situation, which we can simulate, involves finding how many children the family would have to have before there were 3 girls. It should be noted that the geometric trial is a very special case of this negative binomial, because in the geometric we stop at the first success. In the negative binomial we stop at a certain number of successes. Let's take a look at the steps for the negative binomial simulation. Again, you'll notice that steps 1, 2, and 3 are identical to the previous 2 situations. Step 4, though, is quite different. We're going to go until we have a third girl. And step 5 is the same as in the geometric situation. We're going to count the number of children until we got that third girl. So, for example, if you were interested in family planning, I guess if somebody came in and said, look, we'd like to have 3 girls, we want to have 3 strikers for our girls' soccer team, how many children should we expect to have? And again, what you could give them from the simulation is the average. You could also look at the distribution. How often the first 3 children were girls? How often it took 4, 5, 6, 10, 20 children to get those 3 girls? So a simulation is a quick, easy, safe way to get tons of data on a particular situation, provided you know the probability involved, and you can guarantee, in these cases, independence of each event. Now, not always do we have situations that are Bernoulli, but in many of those cases we can provide a simulation. What makes a situation not Bernoulli? Well, for example, the World Series. And here we see some celebration going on after winning the last game. What is the last game of the World Series? Well, it could be the 4th, it could be the 5th, it could be the 6th, it could be the 7th game of the World Series, which means that it's not a Bernoulli trial. Even if the probability of a particular team winning any game stays the same, and winning one game does not change that probability, so they stay independent. And there are 2 outcomes. Either the American League wins or the National League wins. But it's not a fixed number of events, nor do you go until you get a certain number of successes. You go actually until you get 4 successes, but that's limited, because in a Bernoulli situation where you're dealing with either a negative binomial or a geometric situation, you can theoretically go on forever. A World Series cannot go on forever. It must end by 7 games, but it doesn't have to. So that would not be a candidate for a Bernoulli simulation. It can be simulated, and in many cases, it is easier to simulate a World Series than to do the mathematical computations necessary to find the probabilities. Now, why would a baseball fan want to simulate or know the probabilities about a World Series? Well, one can say that perhaps over the history of the World Series, the American and National League teams have been evenly matched, or perhaps they haven't. So if we assume evenly matched and we use as a probability of 0.5 for the American League team winning and a 0.5 for the National League team winning, and we run 100,000 simulations, and we see how many times the World Series in our simulation ended in 4 games, 5 games, 6 games, and 7 games, and we match those percentages up to the percentage of times the actual World Series had ended in 4, 5, 6, or 7 games. If those numbers were relatively close, we could say that our simulation justifies saying that typically the American and National League teams have been evenly matched. On the other hand, if there's a lot more 4 and 5 game World Series when in the real data than in the simulated data, then we might say it appears that the teams were not quite evenly matched. But again, only a baseball purist would be interested in that. But simulations could help that person find the answer to his or her question. Another example, which could not use a Bernoulli situation, but which could be simulated, is the weather. Typically, the weather from day to day is not independent of the previous day's weather. And therefore, the probability of success changes from day to day. This negates one of the important requirements for the Bernoulli situation, the requirement of independence. In a predator-prey situation, and this is generally where you have, for example, wolves and rabbits, or wolves and deer, and you're concerned with the dynamics of the two populations, the probability for survival of the wolves and what they're feeding off of, let's talk about deer perhaps, those probabilities would be dependent upon the number of the opposite type of animal. As there were more deer, more wolves could survive, and the probability of any one wolf surviving would be greater. As the deer died off, then the probability of a wolf surviving would be decreased. And the same would happen as the number of wolves fluctuated in terms of the probability of the deer surviving. So we have a situation where we're not independent, and therefore it's not a Bernoulli situation. The sales simulation used at the beginning of this lecture is not a Bernoulli situation. And the reason is very simple. There were 3 outcomes: no sale, $100 worth of sales, and $1,000 worth of sales. With 3 outcomes, you can't be Bernoulli because Bernoulli requires 2 outcomes. An example of a powerful yet simple use of Bernoulli simulation involves a legal question of prejudicial hiring. Now we're getting into something that is quite real, because we always read about situations where people are suing because in a hiring practice, the company or organization was prejudicial to a certain group of people. Here's the situation. A company is planning to hire 30 new technicians for an expansion of a plant. These are highly skilled and well-paid employees. It is determined that 40% of the qualified applicants are female, and therefore it is expected that the company will hire 12 female technicians. 12 because 12 is 40% of 30. When the hiring process is concluded, only 8 females were hired, and the remaining 22 technicians were male. This is significantly different, it appears, from the 12 that's expected. Now, we know in the real world there's variation, so we shouldn't be surprised if we had gotten 11 or 13, or perhaps 10 or 14. But 8 was the number of females. And someone's going to say that appears to be evidence of prejudicial hiring practices by the company, and a lawsuit is entailed. And in a number of lawsuits, simulations can be used to demonstrate whether or not the plaintiff's case is justified. And one of the reasons for that is typically in a jury and amongst most judges, how many people are there that understand probability theory? And if the lawyer had a statistician come up and explain in a binomial situation with such and such formula the results were this, probably you'd get glazed looks from the members of the jury, and the judge himself or herself might not actually understand what was being said by the witness. But if we provided the results of, let's say, 500,000 simulations and explained how the simulation was done, I believe everyone in that courtroom would understand the results for that witness. So let's go ahead and look at how we would do a simulation for that situation. First of all, we need an N and a P, and we have N is 30, and we have a P. The probability of hiring a female is 0.4 if it's being done at random. And we are going to simulate hiring people at random, knowing that on average 40% should be female. Again, remember, the expected number is 12 females. The actual number is 8. Now, we go ahead and run the simulation. In fact, I did this simulation, and I conducted 1,000 trials. And here are the results of those 1,000 trials. I've only shown you the results for 8 or fewer females out of the 30 people hired. So you'll notice the totals in the second column do not equal 1,000. But if I had shown all the possible results from 4 to the maximum number of females, that would equal 1,000. Obviously, most of the results had 11, 12, 13 females being hired. And we notice there is one case where only 4 females were hired, 4 cases where 5 females were hired, 12 cases in which 6 were hired, 26 situations where 7 were hired, and in 50 of the 1,000 simulations, there was exactly 8 female technicians hired. The results of the 1,000 simulations show that 93 times out of 1,000, 8 or fewer females were hired. We can now talk about the probability of hiring 8 or fewer females. That represents 9.3%. That is 93 over 1,000. 9.3%. Now, the question that must be answered, and this is not an easy question, is 9.3% a rare occurrence, or is it quite common? If you believe that 9.3% is rare, then you would say that the outcome, getting 8 or fewer females when 12 are expected, is rare and a rare occurrence when it's done randomly. And therefore, we obtained a rare occurrence, which means that there probably was prejudice in the hiring practice. If you believe that 9.3% is not rare, not exceptionally large, but still not small enough to indicate a rare occurrence, then you would say there is no evidence from the simulation to indicate prejudicial hiring practices. The 8 females might have been hired strictly due to chance. Now, in the real world, the world of probability and statistics, 5% usually is the largest probability that is used for significant results. If you get 5% chance or less, then you have a somewhat rare occurrence. So in this situation, 9.3% would not be a rare occurrence. And what you would have, therefore, is a situation which is not quite clear. It is obvious that there's no strong evidence that there was prejudicial hiring. On the other hand, there is no strong evidence that there wasn't. Had 40% or 35% of the 1,000 simulations resulted in 8 or fewer females being hired, we'd be happy to say that it appears there was no evidence of prejudicial hiring. Getting an answer between 5 and 10% leads us in a cloudy situation. And now we'll leave that up to the judge and the jury. But indeed, a very realistic situation, a situation where it would be very difficult to get real data, a situation where mathematics of probability being used will be confusing to the people making the decision, the judge and the jury. A simulation provides a real opportunity to look at results and to use those results to make a decision, in this case, the decision in the jury trial. In our next lecture, Lecture 20, we will begin our look at statistics. We will look at data displays and numerical statistics.